Hey students, this is lesson 4.4, graphing a function rule. In this lesson, we are going to learn how to graph equations that represent functions. Go ahead and do the review here. There's a couple of very important vocab words along the way, so make sure you take note of that. All right, we're going to learn how to graph function rules here. This is actually a linear function rule, and you'll start to recognize those, but if you do, when you're filling in a table of values like we're going to do here, as soon as you see the pattern, then you can just follow that pattern. You don't have to compute every one of these. But let's do some negatives and some positives. So let's choose these for inputs. And then our output, I'll put over here, but we need to do negative 1/2 times the x value, which is negative 2, plus 2, negative 1 times negative 1/2 times negative 1, plus 2, negative 1/2 times 0, plus 2. I think after I have 3 of these values, that should be enough for me to see a pattern. Negative 1/2 times negative 2 is 1, plus 2 is 3. Negative 1/2 times negative 1 is positive 1/2 plus 2 is 2.5. Negative 1/2 times 0 is 0 plus 2 is 2. And it seems like these values are decreasing by half each time. So I'm going to just continue that way. And then I want to graph these. So I'm going to have a point at negative 2, 3 right there. Point at negative 1, 2.5. 0, 2, 1, 1.5. And 2, 1. And since I'm not specifying what kinds of numbers this equation is representing, I have to assume that it can represent all real numbers. So I need to connect a line through those and continue it. And note that this is only part of the graph of this. It would keep going continuously. So go ahead, you try that. Okay, graphing a real-world function. When you are graphing a real-world function, you have to think about what values make sense in the problem. The input values that make sense it's called the domain. The output values that make sense is called the range of possible values. So if you look at this column, it says this function represents the total cost of renting a truck for H hours. What is reasonable graphical function, given that the daily limit is 12 hours? So we don't want to do any numbers higher than 12, and I don't want to do any negative input values either, because you can't really rent a truck for like negative 2 hours. So I'm going to start at 0 for my hours, and that's going to be on the x-axis, hours. And then my y is going to be my cost axis. So you can label those over here, cost and hours. And then reasonable number of hours is from 0 to 12. I'm not going to do all of them. 2, 4, 6, 8, 10, 12. And then to find the cost, we need to take 12.5 times my number of hours, and then add 30 for each of these. And I'm going to look for a pattern here and just see what happens. It seems like the cost should go up by the same amount. So my first value is 30. So 0 hours, $30. My second value, 12.5 times 2 is 25 plus 30 is 55. My third value is 12.5 times 4 is 50 plus 30 is 80. And I can see that I keep adding 25. So I'm just going to assume that that pattern is going to continue. So I'm going to get 105, 130, 155, and 180 for costs. And when I graph those, since it's going up by a constant amount, I know that it's going to be linear. So I'm just going to graph a couple of these and then use the idea that it's linear to help me get the rest of it. So I'm going to put these hours here. And for my cost, there's 10 segments here, so I need to divide, well, I need to get all the way up to 180. And so if I went by 10s, I'd only get up to 100. So I'm going to go by 20s. So 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. That seems like I should be able to get all the values. 0, 30 would be right here. Let's do another one. 480 would be right here. And I'm going to do the last one. 12, 180 is right here. And remember I said that this would be a linear function, so I'm just going to draw a little dotted line to help me get the rest of these dots in here. And actually, you could probably rent it per hour. Most places would make you pay at least for an hour's worth of time. So they would always round it to hour, which makes this a discrete function. So I'm just going to put my dots at each hour on this line. And that's going to be my, I'm just going to get rid of that line. Because I don't think you're going to be able to pay for prices in between. So there's a graph of reasonable costs for renting this truck. All right, you try that. Try one of those. Notice when I made my graph, I did put a solid line here, and that's because any number of gallons in between, or any weight and any number of gallons would be possible here. This is a continuous situation, but it would end at 250 because that's the spot capacity. So, all right, new concept here, continuous and discrete graphs. You've heard me use some of these words. A continuous graph is a graph that is unbroken, that any point is possible anywhere along that line. A discrete graph is a graph composed of isolated points. So like if you're graphing all whole numbers or all integers, that's a discrete graph. So this one's a continuous one, and this one's discrete. All right. So let's look at a situation and decide if we think if it's continuous or discrete. Megan buys eggs at a supermarket for $1.75 per carton. The cost is a function of the number of cartons boxed. What is the graph of the function? Should we make it continuous or discrete? So let's let our x be our number of cartons, and our y can be our cost. And any number of cartons makes sense here. And then our cost is $1.75 for one carton. So 0 times 175, 1 times 175, 2 times 175, 3 times 175, and so on. We can just add 175 each time. And I'll do one more. That would be 950. All right. And actually, that last one should be 10, shouldn't it? And then if we're going to graph that, we're going to have 0, 0. We're going to have 1, 175, 2, 350, 3, 350, or 3, 525, 4, 7, and so on. I'm going to use the idea of linear. 10 cartons would cost $17.50. That would be about right here. And I know that it's going to be a linear function, so I'm just going to draw that, and then that'll help me draw the rest of these. But I'm going to remove this line because we can only buy whole numbers of egg cartons. We can't buy in between, so this is a discrete situation. All right, you try that. All right, last problem. What is, we're going to graph this. This is a nonlinear function. For sure, when you do nonlinear functions, you want to make sure you pick some positives and some negatives for inputs. So I'm going to do -4, -3, -2, -1, 0, 1, 2, 3, and 4. Now to do this, my y values, I have to take my x value, and make sure you use parentheses here, because you have to multiply -4 by itself and subtract 1. And that's positive 16 minus 1 is 15. So here's the values I get when I evaluate this equation for those values from -4 to 4. So -4 pairs up with 15, so that's this point right here. -3 pairs up with 8. -2 pairs up with 3. -1 is 0. 0 is -1. 1 is 0. 2 is 3. 3 is 8, and 4 is 15. And this is definitely nonlinear, and since we can use all real values for inputs, we need to graph it like it's a continuous function. So we need to put a line, actually a curve, and those will continue in both ways. All right, that's it for the lesson. Go ahead and do the lesson check to get ready for, oh, we'll do problem 4. I'll give you the answers to that. All right, go ahead and do the lesson check, and I will see you tomorrow in class.